We put two officially obsolete GPUs, a $300 Tesla P40 and a $700 V100, through a test almost nobody runs. What happens when you actually fill the context window? There's a documented crash bug waiting for one of these cards at 24,000 tokens. And along the way, we found one flag, set wrong by default, that was hiding half of both cards' speed. Quick fact check before anything else. NVIDIA's CUDA 13 toolkit dropped compiler support for 3 GPU architectures back in August of last year: Maxwell, Pascal, and Volta. Pascal is our P40. Volta is our V100. So this isn't breaking news. It's about 11 months old, but a lot of people running these cards still don't know what it actually changed. And NVIDIA hasn't looked back. The toolkit is on 13.3 now, with a 13.4 preview already out. All of it touring and up only. Here's what it didn't change. Your card doesn't stop working. A build made with CUDA 12 keeps running on a P40 or a V100 indefinitely. Every number in this video comes off a CUDA 12 build made this week. What it did change? No future CUDA compiler will generate new machine code for either architecture ever again. These cards get whatever's already been built for them. That's the ceiling. So the buy question was never which card is fastest. It's which one is still usable on a real workload, now that the toolchain has permanently moved past it. We own both cards in question, so we ran the test and the results genuinely surprised us. We covered the memory price side of this trade in an earlier video. This is the other half, what that memory actually does once you use it. Let's put faces to the numbers, because the price gap is the whole story. The P40, 24 gigabytes of GDDR5 from 2016. No tensor cores at all. Pascal predates them. 347 gigabytes a second of memory bandwidths, roughly $260 to $330 used. The V100 32 gig PCI Express version, real tensor cores, HBM2 memory at around 900 gigabytes a second, 2.5 times the P40's bandwidth, for about $650 to $750. So the frame for this whole video, the V100 costs 2 to 3 times more at the same rough capacity floor. What does that money actually buy? One gotcha. We hit ourselves. Worth knowing before you buy. The V100 needs a 16-lane riser slot. Not needs it for full bandwidth. Needs it to show up at all. Drop it into the wrong riser slot on a server like ours and it doesn't enumerate. Not NVIDIA SMI. Not in the PCI Express device list. Nothing. It's invisible until it's sitting in a proper 16-lane slot. If you're shopping a used server for one of these, that's a line item, not a footnote. And both of these are server cards, which matters beyond the sticker. Neither has a fan. They're built for a chassis that forces high static pressure air across a passive heatsink, a real server, or an aftermarket shroud and blower. In a quiet desktop case with no ducting, they throttle or cook. That's not a defect. It's what a data center part is. It's also why they're this cheap. Data centers retire hardware in bulk on depreciation schedules, and cards with no display output have a thin resale market. The same wave will eventually reach the A100, but not yet. Today, a used 40 gigabyte A100 still runs around $3,500, and the 80 gigabyte cards sit near 10 times a 3090's price. The next tier up isn't a step, it's a wall. The RTX 3090 is the odd one out, and we want to be precise. We don't own one. Every 3090 number here is sourced from public listings and benchmarks, labeled on screen every time. Used 3090s currently average around $1,250, floor near $1,000. It's a consumer card, powers its own fans. No chassis requirement, no riser gotcha. That's a real point in its favor before a single benchmark runs. Every number comes from the same model, run the same way. The model is Qwen 3.627B, dense, 27 billion parameters, and a hybrid design. 3 out of every 4 attention sublayers use gated delta net, a linear attention method. Every fourth uses standard attention. Hold on to that word. Hybrid? It ends up mattering more than we expected. Quantization locked at Q4km across every test. 17 gigabytes of weights. Build, mainline llama, CPP, fresh this week. Commit hash on screen. The protocol is 3 context buckets. A, 4,000 tokens, the number everybody publishes. B, 32,000 tokens, a full working session, the number almost nobody publishes. C, the ceiling, the maximum context each card actually loads and runs, found by binary search on the hardware, not read off a spec sheet. 2 more switches get tested explicitly, and they turn out to be the whole video: flash attention on versus off, and multi-token prediction on versus off. Every configuration you'll see ran 3 times. We report the median. Before the numbers, the yardstick. And it has 2 parts because a chat has 2 weights in it. Part 1, generation speed. People read at roughly 4 words a second, which lands around 12 to 15 tokens a second. Above that line, text keeps pace with your eyes. Below it, you're waiting on the machine. That's the reading floor. Part 2, and benchmarks skip this one constantly. The wait before the first word. Before a model can answer about a big context, it has to process all of it. That's prefill. And at these context sizes, it's not a detail. It's minutes of your life. A speed chart that only shows generation is telling you half the story. So usable in this video means above the reading floor once it's talking, and a first token wait you'd actually sit through. One more scope note, our numbers are cold starts. Every test paid the full prefill from 0, no cache reuse. In real multi-turn chat, you pay the big wait once per session, not per message. Batch jobs. Summarize a folder overnight. Don't care about any of this. They only care about total time. Now the part we genuinely didn't know the answer to going in. Flash attention computes attention without materializing the full attention matrix. That's why it's standard practice everywhere. But it's built around tensor core math. And neither of our cards has that in modern form. The P40 has no tensor cores at all. The V100 has generation 1, an older instruction set. On both, llama.cpp routes flash attention through a fallback path called vec, a slower route that exists so old cards can run it at all. And there's a documented crash on that path. llama.cpp issue 22032. Flash attention on Pascal. Hard crash mid-generation past roughly 24 to 26,000 tokens of context. That bug was reproduced on a big mixture of experts model. Ours is a dense hybrid. Nobody had published whether it carries over. So our ceiling test doubled as a trap. Push the P40 straight through the crash window with flash attention on and film whichever thing happens. There's one mechanical coupling to know before the results, because it shapes everything. In llama.cpp, turning flash attention off also forces the cache to full 16-bit precision. Quantized cache requires flash attention, so flash attention off always costs extra memory on top of whatever it costs in speed, or whatever it gains. Hold that thought. Multi-token prediction merged into mainline llama.cpp this year, and beta, off by default, enabled through a speculative decoding flag. Qwen 3.627b ships the extra prediction head it needs, so it's supported, not a hack. The model drafts several tokens ahead and verifies them in one pass, and the flag that controls how many it drafts defaults to 3. We swept that number, 24816, on camera, on both cards, at every context depth. Here's the P40 at 4,000 tokens. 13.6 tokens a second with it off, right at the reading floor. 32.1 with it, set to draft 8 tokens. That is more than double from one flag, on a card with no tensor cores from 2016. And notice, 16 is slower than 8. Draft too far ahead and the model starts guessing wrong, and rejected guesses are wasted work. There's a real optimum. The default, isn't it? And nobody publishing peak numbers would ever find it, because it only matters when you tune past the defaults. The catch you should expect: acceptance. About 2/3 of drafted tokens were accepted in our runs. That ratio, and all of this speed up, will move with your workload. Drafting works better on some text than others. Our numbers are our workload, measured. Yours will rhyme, not math. For scale, community reports on newer consumer cards claim roughly 1.5 to 2 times from the same feature. Reported, not ours. What we measured on our own obsolete silicon is at the top of that range. Now let's fill the context up and see what survives. Context B, 32,000 tokens loaded. This is where the two cards stop being versions of each other and become different machines. The P40 barely notices, 12.5% off its short context speed, 11.9 tokens a second at defaults, which, note, is now below the reading floor, and 24.8 with multi-token prediction at 8. The $300 card at 32,000 tokens of context, comfortably readable. One flag. The V100 falls off a cliff. 53% of its speed gone. 31.9 down to 15.1 at defaults. Still readable, barely. But here's the uncomfortable math. At defaults, at 32,000 tokens, the card that costs 2 to 3 times more is only 27% faster than the P40. That premium you paid for deep work? At defaults, it mostly isn't there at depth. Then it gets stranger. On the V100 at depth, drafting 16 ahead beats drafting 8, 36 versus 29 tokens a second. The optimum draft length moved when the context got deep, and it moved exactly the way the theory says. When each verification pass is expensive, you want to amortize it over more tokens. And the strangest result of the whole bench, the fastest 32K configuration on the V100 has flash attention off, 39 to 40 tokens a second. Flash attention off, multi-token prediction on. We didn't believe it either. We reran it twice and read the output by hand to make sure it wasn't fast garbage. It's real and it's coherent. And before you blame the card, don't. We've profiled this exact model on this exact V100 with NVIDIA's own tools, and the time disappears into flash attention code paths that were never tuned for Volta. The code literally falls through to a configuration built for newer GPUs, past a comment that says, "TODO, tuned specifically for Volta." When we hand-tuned just 9 lines of that configuration, prefill jumped 22% on this card. The cliff is soft. The silicon has headroom nobody shipped. We're digging into that properly in a coming video. The deep dive is already on our bench. For today, the practical takeaway is that the doctrine is card-specific. On the P40, flash attention on, always. It's worth up to 2 times at depth, and the quantized cache saves 5 gigabytes. On the V100 at depth, flash attention off is the speed play, if you can spend the memory. And the wait for the first word? This is what the V100's money actually buys. Pre-filling those 32,000 tokens took the P40 about 3 minutes. The V100, 53 seconds. That gap never degrades, never needs tuning, and you feel it every time you load a big context cold. Generation speed you can fix with a flag. The wait, you cannot. Context C, the trap. We marched the P40 up through the crash window with flash attention on, 20,000 tokens. Passed. 42,000, passed. 54, 60, 64,000, passed. 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 The documented Pascal crash never fired. Not once in either flash attention mode, all the way to 64,800 tokens, where we stopped the search, not the card. To be clear about scope, the bug is real, it's open, and it was reproduced on a mixture of experts model. On this dense hybrid, it does not trigger. If you run models like this one, that crash is not your problem. What we found instead was the actual reason this architecture is interesting on old cards. The hybrid's memory cost barely grows. Going from 4,000 to 65,000 tokens of context cost the P40 about 2 gigabytes of extra cache. 16 times the context, 2 gigabytes. The whole 24 gigabytes can't do deep context assumption is just false for this class of model. The P40 hit our search limit with 6 gigabytes to spare, still generating at 10.4 tokens a second, 15.3 with the draft flag. The V100 went further, 130,000 tokens, our cap again. Still coherent, still 16.5 tokens a second with drafting on. We found exactly one real wall in this entire bench. Flash attention off on the V100. The 16-bit cache finally overflowed 32 gigabytes at about 122,000 tokens. Genuine out of memory, error in the log. That's the trade for the V100 speed trick printed in hardware. Flash attention off is faster at depth, and it's also the only configuration that ever actually died. One honesty beat before the verdict. Reaching a ceiling and living there are different things. At these depths, both cards are minutes of prefill from the first word. 7-ish minutes for the P40 at 65,000. 6 for the V100 at 130,000. That's fine for a batch job, and brutal for a conversation. The spec sheet ceiling is real. The conversational ceiling is wherever your patience runs out. Now, the money math. Take each card's price. Divide by what it actually sustains at 32,000 tokens. The deep bucket, the one that resembles real work in its best real configuration. The P40, $300, 24.8 tokens a second, about $12 per token per second. The V100, $700, 38.7, about $18. The reported 3090 number, plain llama.cpp, short context, because nobody has published a deep context number under a protocol like ours, is around 40 tokens a second, call it $1,250 for $31 per token per second. With the caveat on screen, that's its best bucket compared against our card's hardest. Even spotted that advantage? It's the most expensive way to buy this speed. Run the same math at defaults and the picture flips harder. The P40 costs about $25 per token per second, the V146, which is the quiet thesis of this whole video. The cheapest speed in this market isn't a card. It's knowing which flags to set on the card you already have. So, 3 cards. The P40 at $300 is the value verdict of this bench. With conditions, tuned. It reads comfortably at any depth we could reach. It never crashed. And its memory headroom at depth embarrasses its reputation. Its real weakness isn't speed anymore. It's the 3-minute cold start at depth, and the server chassis airflow it needs before it runs at all. The V100's premium buys exactly one thing at depth, and it's real. The wait. 3 times faster to the first word, every time, and no flag can tune it away. If your work is loading big, cold contexts all day, that's what the extra $400 is for. Its generation speed at depth, though, needed a counterintuitive setting to beat the P40 by as much as the price gap implies, and that setting is the only thing in this bench that ever hit a real wall. Remember, that's a software story, not a silicon one. The card is waiting on code nobody tuned for it. The reported 3090, the convenience buy for a desktop. It cools itself, but it isn't plug and play everywhere. It wants its own 8-pin power leads from the supply, and it has no business in a server chassis. In the case, it was built for fast and per dollar, per token, at real depth. The numbers we can compare say it's the expensive path. If someone runs a 3090 through this exact protocol, deep buckets and all, we'll link it below. That number doesn't exist publicly yet. And whichever card wins your budget. The chassis, the riser slot, and 2 minutes of flag reading are part of the real price. The defaults cost the P40 half its speed, and the V100 most of its deep context premium. That's the test almost nobody runs. And now you've seen it run. We run these numbers ourselves. That's what the tested tier means here. The full protocol, every flag, every raw log is in the linked repo. Change one card and rerun it. If you run a P40 or a V100, tell us your numbers in the comments, especially if your workload moves that draft acceptance rate. And if there's a card or a model you want, through this same 3-bucket protocol, say so below. That's how the next one gets picked. Subscribe if you want to see it.